Hi, this is the next installment in the series of videos where I solve the free response questions to this year's AP Statistics exam. Check the description section for links to my solutions to the other questions. For this question 6, I benefited a lot from discussions with other AP readers, especially with Jay Windley at Cal Poly Pomona. So I'd like to thank Jay Windley for that. His contributions helped a lot with part B and part D of this solution. I hope I understand his ideas correctly. So if there are any errors, those are mine, not Jay's. Question 6. Question 6 on the AP Stats exam is always what's called an investigative task, where you're led through the steps that allows you to discover some kind of statistics that is outside the typical AP Stats curriculum. A jewelry company uses a machine to apply a coating of gold on a certain style of necklace. The amount of gold applied to a necklace is approximately normally distributed. When the machine is working properly, the amount of gold applied to a necklace has a mean of 300 milligrams and standard deviation of 5 milligrams. The necklace is randomly selected from the necklaces produced by the machine. Assuming that the machine is working properly, calculate the probability that the amount of gold applied to the necklace is between 296 and 304. Assuming the machine is working properly, if it's working properly, then first of all, you'll be normally distributed. Actually, approximately normally distributed comes before when the machine is working properly. So it's going to be approximately normal all the time. When it's working properly, the mean is 300 and the standard deviation is 5. Question A is a normal distribution question. Well, for any probability distribution question, they want you to show the distribution by name or formula, the parameters that define that distribution, and the interval over which you're calculating your probability. People usually don't identify the normal distribution by formula. That happens a lot more often with the binomial distribution. People would just usually define by name by writing the word normal or using the math notation capital N. The parameters that define the normal distribution would be mu and sigma or sigma square if you're used to doing that. And then the interval of the probability would be things like x is greater than a certain number or x is between some two numbers. And then a lot of times they would accept a well-annotated graph as showing all of this information. Let me show you how to do that with a graph. You draw something that looks kind of bell-shaped. A lot of rubrics in the past have accepted it as drawing a normal distribution. So by doing this, I've shown the interval where the probability is calculated on. I need the mean and the standard deviation. And while here, even though I said a bell-shaped curve would be acceptable, just to be on the safe side, I'm going to write the word normal. Alternatively, I can say that the gold amount is distributed according to the normal distribution. And then I have my interval by writing P open parentheses and then the two numbers. And the answer is 0.576. Next page. The jewelry company wants to make sure the machine is working properly. Each day, Cleo, a statistician at the jewelry company, will take a random sample of necklaces. Each selected necklace will be melted down and the amount of the gold applied to that necklace will be determined. Because a necklace must be destroyed to determine the amount of gold that was applied, Cleo will use random samples of size n equal 2 necklaces. That sounds a little bit different from class already, right? In class, we never do things with samples of 2. It's always like a very large number. Cleo starts by considering the mean amount of gold being applied to the necklaces. After Cleo takes a random sample of n equals 2 necklaces, she computes the sample amount of gold applied to the 2 necklaces. Part B, suppose the machine is working properly with the population mean amount of gold being applied of 300 and standard deviation of 5. So part I, calculate the probability that the mean amount of gold applied to the sample, to a random sample of n equals 2 necklaces will be greater than 303 milligrams. All right. Even though we have a very small sample size, n equals 2, in this case, central limit theorem still applies because the population distribution of the gold is given as approximately normal. By the central limit theorem, we can use normal distribution to calculate this probability. And again, normal calculation requires all of these identifiers. So let's make sure we do that. But before we do that, we have to justify using the central limit theorem and applying normal. So let's do that first. The sampling distribution of means is approximately normal because the original distribution is given as approximately normal. By the central limit theorem. And now we can determine the sampling mean and the sampling standard deviation. Sigma over square root of n. And now I'm doing all the identifying necessary for normal. I'm pretty sure I don't really have to do that because I already have the word normal here. I already have the mean here, and I already have this standard deviation here. But might as well. Greater than 303. And I get 0.1980. Support II. Suppose Cleo took a random sample of n equals 2 necklaces that resulted in a sample mean amount of gold applied of 303. Would that result indicate that the population mean amount of gold being applied by the machine is different from 300? Justify your answer without performing an inference procedure. Well, as a test taker, what do I do when they tell me not to do something? Well, I do it on the side. If I'm testing that the population mean amount of gold being applied by the machine is different from 300, then that means my H naught is that mu equals 300, and H A is that mu is not 300. The sample mean is 303. The z-score of this would be the test statistic. And this probability that I already calculated up here would be the p-value on the right side of it. This is the probability of getting a sample as extreme as ours. And extreme as ours is 303 or more. So that's the p-value. Now, however, the HA is that mu is not equal to 300. It's a two-tail test. So in order to do that, I need another tail on the left. And the total of the two of them will be my p-value. Well, one side is 0.198, so two sides must be 2 times 0.198. And then I can answer the question that way. But I'm not allowed to conduct an inference procedure, so I will quietly erase this. And I do everything that I would have done, but I would do it in words. I will pretend I didn't do it. So instead of using the word p-value, I will use a phrasing that means the same as a p-value. Specifically, the probability of getting a sample as extreme as ours. Per part BI, probability of getting a sample as extreme as ours on the higher side is 0.198. Therefore, the probability of getting a sample as extreme as ours either side is 2 times that, 0.396. Therefore, it is not an unusual event, assuming, remember, I have to get this into a definition of p-value, assuming H naught is true. Basically, I'm saying that p-value is too high and H naught is not rejected. You don't reject H naught. Now I make the conclusion in context the same way I would have done inference, except I don't write out the actual inference because it tells me not to. Continue to the next page. Now Cleo will consider the variation in the amount of gold the machine applies to the necklaces. Because of the small sample size, n equals 2, Cleo will use a sample range of the data for the 2 randomly selected necklaces rather than sample standard deviation. Here's the investigative part. The part where you do inference on the range, which is something we've never done before in class. Cleo will investigate the behavior of the range for samples of size n equals 2. She will simulate the sampling distribution of the range of the amount of gold applied to the 2 randomly sampled necklaces. Cleo generates 100,000 random samples of size n equal 2 independent values from a normal distribution with mu equals 300, sigma equals 5. The range is calculated for the 2 observations. The simulated sampling distribution of the range is shown in graph 1. This process is repeated using sigma equals 8 as shown in graph 2, and again using sigma equals 12 as shown in graph 3. So here's graph 1 with sigma equals 5. Graph 2 with sigma equals 8. It seemed to be spread out a little bit more to the right. And graph 3 with sigma equals 12 is spread out even more to the right. Part C, use the information in the graphs to complete the following. Subpart I, describe the sampling distribution of the sample range for random samples of size equal 2 from a normal distribution with standard deviation sigma equals 5 as shown in graph 1. That's a very fancy way of just asking for this. Describe the distribution. How do we describe the distribution? Shape, which consists of 2 things. How many modes? Unimodal, bimodal, etc. And skewness. Center, spread, and any outliers. Unimodal, 1 mode, skew to the right, center, down here somewhere, and the spread. Well, normally you could describe a spread as standard deviation, but in this case, it's kind of hard to see what the standard deviation could be. So let's define the spread by where most of the points are. Most of the points are between those numbers. By the way, it's not the complete range because in theory, there are probably like some dots all the way going all the way out to infinity. Because if you think about picking 2 points from a normal distribution and calculating the range, it's totally possible that the 2 points are at like 1 billion positive and 0. So don't talk about the range because it's, I don't know if they'll mark you wrong for it, but it's actually not accurate. So I'm going to say that the vast majority of points are between 0 and 20. First, I'm going to copy down verbatim. Appears to be unimodal, with center around 5 to 9. There are outliers at sample range greater than 20. Part II, describe how the sampling distribution of the sample range for samples of size n equals 2 changes as the value of the population standard deviation sigma increases. If you compare again at the beginning, it's like sigma equals 5. At sigma equals 8, it spreads out more. And at sigma equals 12, it spreads out even more. So that's what I will say, but I will also need to repeat everything else as well. The shape, the center, the spread, the outliers. Being unimodal and skewed right don't change, so I need to say that. But as the spread increases, the center also moves along with it. And then where the outliers are also moves further to the right. When sigma equals 8, the center is down here somewhere, maybe 10 to 15. And when sigma equals 12, center maybe, so 15 to 20. And the spread also increases. At sigma equals 8, it goes almost all points are between 0 and 30. And at sigma equals 12, almost all points are between 0 and 40. Outliers are at higher values as well. Next page. Cleo takes a random sample of 2 necklaces and calculates the sample mean amount of gold applied as 303 and the sample range as 10. Part D. Recall that the machine is working properly if the amount of gold applied to a necklace has a mean of 300, standard deviation of 5. Subpart I. Consider Cleo's range of 10 from the sample size n equals 2. If the machine is working properly with a standard deviation of 5, is the sample range of 10 mg unusual? Justify your answer. If the machine is working properly, then sigma equals to 5. So let's go look at the sigma equals 5 graph. Here's 10. It's unusual if it's rare for us to find a sample that extreme. Therefore, we need to look at this area. It doesn't look like 0.05, right? 0.05 is 1/20. That doesn't look like 1/20th of the graph. In fact, if I try to draw that area, it looks like about 1/5 of the graph, or maybe 1/6 of the graph. I'm going to pick a number. I'm going to say 0.15. On graph one, probability that the sample range appears to be about 15%. And again, we're using the language of p-value without actually calling it a p-value. It is not unusual. Part II, do Cleo's sample mean of 303 and range of 10 indicate that the machine is not working properly? So the question is, if it's working properly, would it end up with a sample mean of 303 and a range of 10? So we need an end in there. If the machine is working properly, then the probability of a sample mean as extreme as 303, actually as extreme as Cleo's, in either side is something we already calculated in part B, 0.396. And the probability of sample range is about 15–20%. And that's from part D. Well, DI right here. So the probability of getting both of these is the product of these two. And when you multiply, you get 0.0594, which is kind of high because we usually go by 0.05. And you're probably going to say, well, how can we multiply? How do we know that mean and range are independent? Well, mean and range are independent because once you have a mean somewhere, just like move the range accordingly. They don't change each other's probability. But how would you as a student know this? And for this, I benefited a lot from discussion with some of my fellow readers, specifically Jay Windley from Cal Poly Pomona. And so I'd like to thank Jay Windley for that. If you don't know the theory, you can tell by this problem, because this problem tells you that Cleo analyzes range based only on sigma. But analyzes the mean based on mu. And therefore, we're justified in using the multiplication. And therefore, there's not sufficient evidence the machine is not working correctly. Well, that's the end of question 6. If you have any comments or questions or any feedback on how I answered this question, which was pretty tricky, please leave in the comments below. Also, check the description section for my solutions to the other questions of this test. Like, share, and subscribe for more content. And thank you for watching. Bye.